All right, so we need to confirm at least one zero within the interval given. Okay, so remember, at least. It could have more, but we have to find at least one. And so what are you going to do? Well, we're going to plug in our values. We're going to plug f of 1 in, and we're going to plug in f of 5. So 1 here is going to be 1 to the 5th minus 2 times 1. Well, 1 to the 5th is 1. And then here's going to be minus 2, and so that gives me a minus 1. Okay, so when I do this one, hopefully we're going to get a positive. So if we do that, we have 5 to the 5th minus 2 times 5. Well, 5 to the 5th is 3125 minus 10. So that's going to be 3115. Well, guess what? Those are opposite signs. Therefore, there is a 0. Let's just erase that. Between 1 and 5. Okay. So that's all it asked for. Now we could, have been given another number. What if we said have an x equals 2? Now, what we would do is we'd plug in 2 for x and see if there's something between 1 and 2. And we could also look in between 2 and 5. So if we do that, let's plug that in here. And this is just off the cuff here. So let's say f of x, or f of 2 rather. Why am I putting that when I want to look at the 2? All right, so we're going to plug in here as 2 to the 5th minus 2 times 2. Well, 2 to the 5th is equal to 32 minus 4. And so that's going to give us 28. Okay, so between these two, there is a 0. So they're opposite signs. So there is a 0. How do I want to write that? 0 between the 1 and 2. But because these are the same signs, there's not going to be a 0 here. So I got lucky. I could have chosen one where, one between 2 and 5, but not 2 and 1. But I chose one, then it was actually between these two, but not between these two. Okay. So that's kind of something that you could do as well, and see we have a degree 5, so it's going to have multiple zeros here. So I just chose something in between there to see if there's something else. So we have, 1, 2, 3 there at least. All right, so what about this one? So we have a right circular cone. So what's a cone look like? I think it's going to look like that, sort of like an ice cream cone. Now we just need the topping on top for the ice cream, and we have it. So what do we have? Well, we have a radius. And the radius is 3x plus 6 centimeters. Now the height, that's from the top down here, and that's 3 centimeters less than that. So if we subtract 3, that's going to be 3, so that's going to be 3x plus 3. Now what do we have? Well, luckily they give us the function for volume because I don't know that off the top of my head. And so volume is equal to 1/3. Well, let's not write it here like that. Let's write it in the function form that we're going to use. So it's going to be v of x, since we called it x, equals 1/3 pi times r, 3x plus 6 squared, times height, 3x plus 3. Okay. So we've written the volume of the cone as a function, and that would be, of course, it's going to be centimeters cubed. And so that would be the factored form of the function. Now, if they want us to have it in the full blown out non-factored form, then we're actually going to have to multiply all this out. And so I think I see something I want to do here. If I rewrite this as 1/3 times 3x plus 3, then times pi times 3x plus 6 squared, I can take and distribute the 1/3 here, and that just gives me x plus 1. So that simplifies that part. But now I have to still square this and FOIL it. So that's going to be 3x times 3x is going to be 9x squared. 2 times 3 times 6, so that's going to be plus 36x plus 36, and then parenthesis. Now I can say, well, now I'm going to take x times each one of those and 1 times each one of those. So I have a pi left out in front. And then I have times, and I have 9x cubed plus 36x squared plus 36x. Now I have plus 1 times all those, plus x squared plus 36x plus 36. And so I'm kind of doing it as kind of adding top to bottom. So that's going to be v of x equals pi times 9x cubed plus 37x squared plus 72x plus 36. Okay, and then that would be my final kind of thing here. Now, wait, did I do something wrong here? I think, because I'm thinking. All right, so I see what I did. When I took 1 times 9x squared, I got x squared. My 9 disappeared. So that was, I was like, that doesn't look right. All right, so 9 and 36, so that's going to be 1 up, so that's going to be a 45. Now, what I could do here and say I'm done here. You know, I could say that was 1, that would be a function. Or if I look, there's a factor of 9 in all of those. And so I could say v of x equals 9 pi times x cubed plus 5x squared plus 8x plus 4. And that could be another function. So I've got 3 different ways I could express this. And again, if we're putting our units on here, that's always going to be centimeters cubed. And so, you know, this would be one. This one we simplified down and got it all in here. But then I saw that there was a 9 in here. I saw a 9 and a 72 and a 36. So I thought that this probably would have something. And it was. I just somehow my 9 disappeared. And so then I'd have this as a final possibility here. Okay, so those are the 3 possible ones. If you got any of those, that would be correct. I think if I wanted you to get to this one, I would have to say not in factored form, and then you would have to multiply it out, and then that would be this one. And now this one is, you know, we factored out that thing, so we had that first term, and that's not a problem, you know, because that's going to give us, you know, it's going to be k is going to be greater than 0. We have an odd function. And so we know it's going to look something like that, at least on the ends up here and down here. And in the middle, then we'll have those points there where we're going to go up and down and stuff. But you know, those end behavior is what we're going to get based on this value here. All right, so let's do another one. All right, so we have a square has sides of 12 centimeters. We have another squares cut out of the corners, and then the sides are folded up to create an open box. Express the volume of a box as function in terms of x. Find the sizes of the squares that should be cut out to maximize the volume enclosed in box. Okay, so let's do this again. So this time we have a square box, and that's 12 by 12. And we're cutting out squares of x plus 1 by x plus 1, x plus 1 by x plus 1, x plus 1 by x plus 1, and x plus 1 by x plus 1. So when we get done, we get some funky shaped thing, and it's going to be 12. And now these are going to be weird because, you know, we're taking x plus 1 times and subtracting it twice. So if we have x plus 1 times 2, that's 2x plus 2. And we're taking 12 minus that. So each side is going to be 12 minus 2x plus 2. And so that's going to be 12, all right, 12 minus 2. So that's going to be 10 minus 2x, okay? So each side is going to be 10 minus 2x. So that's how we're getting the sides now. So with that, we have 10 minus 2x by 10 minus 2x by x plus 1. All right, so our volume based on x is going to be the length, which is 10 minus 2x, and the width is 10 minus 2x, and somehow I can't write, or it doesn't write on here right, times the x plus 1, okay? Now these are going to be, again, centimeters cubed. All right, well, this is really just 10 minus 2x squared times x plus 1, okay? And so that's kind of, if we wrote it out, that's really what it would be. Now what we have to do is go ahead and multiply everything out and go down and get our final volume function. And so 10 squared is going to give us 100. 10 times 2 is going to be minus 20 times 2 is going to be minus 40x. And then plus 4x squared, and then times x plus 1. All right, so now we'll have x times 100, so that's 100x. The next times that's a minus 40x squared plus 4x cubed. Then we have plus 1 times that. So we have, okay, well, we should have rewritten this the other way, but then we'll have plus 100. And then 1 times that's going to be minus 40x. Where's the x's? And then we'll have plus 4x squared. Okay. And so when we get all that done, we're going to have a 4x cubed, if we rewrite it. And then we'll have minus 40x squared plus that, so it's going to be minus 36x squared. And then we have 100 minus that, so it's going to be minus 60x. And then we have plus 100. Okay, so now we've got all that, the cube, the squared, x, and 100. All right, so that's going to be our function, and it's going to be centimeters cubed. And so that would be what we're going to plot in our calculator, because now what we have to do is go to our calculator and type that, type that in and figure out the maximizing. All right, so y equals, now we had 4x to the third, and then we had minus 36x squared plus 60x plus 100. And now we graph that. Okay, so now we need to have our window go out further to the right. So let's go out to 20 and do it by 5. See what we get there. All right, so that's our graph. We need to maximize that point there. So we're going to go second trace, maximize, which is 4. Now we want our left bound. So where are we at here? So that will be our left bound. Our right bound will be on the other side. And we're going to guess somewhere in the middle. And so our max is going to be x equals, I'm going to call that 1. And our maximum volume is going to be 128. All right, so from the calculator, we have x equals 1 centimeter, and the volume max equals 128 centimeters cubed. Okay, so that's my max volume. That was, oops, what am I doing? I got the wrong page here. Somehow. There we are. That looks better. Now, from the calculator, I got x was equal to 1 centimeter, and the volume max was equal to 128 centimeters cubed. So that was my max volume. Now my square is x plus 1 plus, so it's x plus 1, or 1 plus 1 is 2. So it's going to be a 2 by 2 centimeter box is what we have to cut out. Okay, so those are the sides. So it's going to be 2 up, and so each of these boxes is 2 by 2. So the 2 centimeter by 2 centimeter box is what we have to cut out. So that's our equation, our volume max, and our size of our box that we cut out. All right, so that's all I have for this section.